All right, so this is on the origin of the combined gas law, and to understand it, first we need to remember the ideal gas law, which states that the pressure of an ideal gas times its volume divided by the number of moles times the temperature is always equal to this constant R. Really doesn't matter what size container, what the temperature, for the most part, this is going to hold up. Just like for any circle, if you take the circumference of the circle divided by the diameter, you always get pi. You take any gas and take its pressure, volume, moles, and temperature, plug into this equation, you always get the same value R. So let's picture two gases, and one is in a container, a large container, let's say, and the other is in a relatively small container. We can call this gas 1, we can call this gas 2. So now, knowing this, what we're going to do is, let's say we knew the pressure of all these things. So this is, we'll call this P1, we'll call this V1, we'll call this T1, and we'll call this N1. So these all represent the pressure, volume, temperature, and moles of gas 1. Over here I have P2, V2, T2, and N2. And again, these are all describing the gas inside this container. Well, it doesn't matter that these are very different containers. For example, these could be at very different temperatures. This could be at 400 Kelvin. This could be at 10 Kelvin. It doesn't matter what they are. But for both of these containers, we know that P1 times V1 over N1 times T1 equals R. Likewise, P2 times V2 over N2 times T2 equals R. They both equal the same thing, this constant R. So knowing that, we can actually set these equal to each other. We can say that P1 times V1 over N1 times T1 equals P2 times V2 over N2 times T2. So we can set the two gases, even though they're totally different gases, equal to each other. Now, this law, as it's written now, is not commonly used. Because usually we use this law to describe a certain gas where we just change the conditions. In other words, I have a gas in a container, and then maybe I can press the container and make it smaller, and then ask what is happening to the gas. Or I have a gas in a container, and then I heat it up. And so usually we consider the moles to be constant. In other words, we say that N1 will usually equal N2. In other words, no gas is escaping and no gas is entering between state 1 and state 2. And so if that's true, if N1 equals N2, then the N actually can cancel out of the equation, giving me this, the combined gas law. The pressure volume divided by the temperature equals the pressure volume divided by the temperature of the other state. And the only requirement here, as always, temperature must be in Kelvin, or this will not work. The pressure and volume can be in any units as long as they match, but temperature must be in Kelvin or this will not work. And there are variations on this combined gas law. For example, if I have two containers and let's say I have a gas in a rigid container. So here's the gas at state 1, here's the gas at state 2. And let's say here the gas was at a temperature of 200 Kelvin, and here was at 400 Kelvin, and I wanted to figure out how did the pressure change from state to state, but it was a rigid container. Well, that would mean that V1 was equal to V2, and if that were the case, in this equation, I could cancel, and I could end up with P1 over T1 equals P2 over T2. In other words, because if V1 is equal to V2, they will cancel on both parts of this equation. So there are actually three different laws you can get from this law itself. But as long as you know this law, you can pretty much get any of those from it. So that is where the combined gas law comes from, and we'll do some problems in another video.